Okay, we were looking into mobility of carriers and looked into a variety of techniques and varieties which we have seen in mobility. One of the things we said that the mobility is something related to 2 tau minus star. I also said the M star is not same as M star potential states. These values are different, which are called gradual transfer mobility parameters. And I think this course will not talk too much about that. Just say they are much different from the mobility of the function, where M star is essentially related only to PK diagram curvatures. Here, voltage, actually M star is a tensor, D by D tensor. So some other day, some other course, you will graduate, or elsewhere you are abroad or anywhere else, they will teach you what this M star has 9 values. So something which is different from this called conductivity mass or mobility mass, which is not same as voltage mass. So don't use those 1.1 values here. And if I give you actually if I need what is the M star for electrons and volts in the case of mobility variations. Okay, so just to say something more, I could say if this tau gets linked to time, and there is something we said, this occurs because there are electrons which are volts which are accelerated by beams or by thermal vibrations. These accelerated carriers actually hit the atoms, direct atoms. They may hit the electrons themselves or volts themselves, which calls carrier scattering. They can also be influenced by electric field. They can be influenced by impurity atoms. So there can be a lot of scattering events. So in general, when we really talk about tau, this is tau effective. Could be tau collisions with lattice, plus tau collisions with impurities or phase charge. Plus 1 tau due to the field, plus 1 tau due to carrier, and there are many more surface scattering, other scattering events occur. The actual value of tau is 1 upon all of them. So which one will dominate among them? No, not the number. But numerically, which one will dominate? The smallest among them will be dominating. Is that correct? The line probability the smallest time, 1 upon that will be the highest value. So normally at a given time, given process, there will be one of them will start doing. So at different conditions, you may have tau different because one of them, or sometimes they will be closer by the 2 of them. But not all 4 or 5, 6 of them will simultaneously actually influence the tau. And therefore the mass. So therefore the So this is an interesting feature because this is used in variety of devices. This fact that I can change mobility at certain points or certain conditions is useful parameter. Then okay, I have some control. So this is something which is, of course, something will happen which you don't like. It will still happen. So something you can at least change the need at times. So this is what last time I said. One more thing I forgot to say last time, that if I plot the mobility versus temperature, so I see something very interesting curve. This gives me a slope of some proportionality of e to the power 3/2, where this gives me e to the power minus 2. It is found that if the temperature is large enough, that is, let's say some critical temperature if something is larger than this, DC mobility starts decreasing as temperature decreases. This can be attributed to the fact that at higher temperatures, the kinetic energy of carriers itself is higher, and also the lattice vibrations will be also stronger. In fact, the vibrations will be stronger, so there will be more likely interactions between the carriers and the lattice because they are energetic, become faster, and they see something stopping them to hit. So probability effect is much stronger in the case of higher temperatures with lattice. Therefore, one can say that this region is lattice scattering limited. Limited means this decides. That decides how much it will be. It shows decreasing. However, if you start looking at very low temperatures, the electron energy or fuel energy is very low because there is no KT available to them very much. So is the impurities which are lattice because is not vibrating at very low temperature, very low energy charecteristics, and even the impurities which are mainly ionized like that also do not have sufficient energy because the temperature is extremely low. So though the possibility of that electron can move freely because they are not moving, but they themselves cannot move very much because they themselves do not have sufficient energy. As the temperature increases, the carrier energy increases, but still that energy is not sufficient, that temperature is not sufficient for lattice to migrate presently. However, impurities may start now, still not be actually excited because the temperature is not very high. So what happens that impurity, since electrons are excited or carriers are excited, they can move faster, so their mobility starts increasing. However, as temperature reaches, otherwise it could have been much like it could have not even something like this, but in increase and it will start increasing the mobility, but it doesn't because at the certain temperature ahead, impurities also start ionizing themselves, and then they interact with energetic carriers, and therefore mobility gets limited by impurity scattering. So this region is called impurity scattering limit. Impurity atoms. I again say that the word limited, I am saying it is decided by. If you are saying the word limited means limited by how much scattering you have.
So can you explain this graph and security practice?
Okay, fine, no problem. If the temperature is very high, the lattice can vibrate very succinctly. That means there are large acoustic energies now. Since they are vibrating very highly, and I showed you three possibilities. Electrons are also excited, but carriers are also excited. So there is much more chance of collision between lattice atoms and the carriers. As they hit, they lose energy. And if they lose energy, you say they are less mobile. So when the temperature starts rising heavily, the mobility starts decreasing. If you say the other side, which is the critical temperature beyond this, at very low temperatures, KT energy for carrier is very low. That way. But so is ionized impurity atoms also have no energy left with them because they are very low temperature. Most of them will not be ionized. That way. At very low temperature. So you know ionization requires some energy to ionize. They will not even ionize that time. So they will not really scatter with ionic electrons. Lattice is not vibrating because the energy given to temperature is very low. So electron starts, as you increase temperature, electron starts getting clearer and clearer and start moving. And since as larger the temperature there, he said there will be much more energy available for easy to move, therefore mobility starts rising. But as the temperature starts rising further, even the impurities now can get ionized, and now they have electrocoulombic fields around, and therefore now charge carrier coming to them may interact, and therefore the mobility will further start increasing as temperature reaches temperature. Is that point correct? Initially the mobility was rising, but you can see it is started increasing then because the impurities start interacting with carriers. Therefore mobility starts increasing. To some extent, the further temperature, that starts vibrating more, it further reduces the mobility. Is that clear? So this is how mobility curve is seen, that at very low temperatures, mobility is very low.
The reduces means the carrier interact with the impurity.
What it is like, when I interact, I lose my energy. Is that correct? That means I cannot do faster now. Is that correct? So I will be less mobile. So mobility has a temperature dependence. So why am I showing you this graph? Because this interesting feature is that when the device is being operated, many a times you may cool the device for what we call reduction of noise. Okay, many devices are really cooled by us. But cooling may itself may have something else, not always a good effect because mobility may decrease. If you are too much high temperature, and if the device is heated to 150 or 160 degrees centigrade, you may further see that okay, not only the other currents and heated currents are increasing, but also you suddenly find the carrier mobility is there. So there are issues that when to operate where and what will be its influence on the current. While I am interested, I keep telling you, mobility is deciding my bit current. So I want to know at a given temperature how much mobility I have, so that this much current I can get out of the gas. So I am not just for the sake of this, so that is say what I am interested because I want to know where I am and what currents I can actually take out of the gas. Is that correct? Please remember, all the effort we are doing in this course is to tell you very clearly that I want to control device currents or circuit currents by a given proportionality to the voltage. This is all that electrical wants to do. We are not interested otherwise with carriers, with the scatter, don't scatter, they give or they don't give. But you become interested because, oh, then if I have to control, and how will I control, and what is the physics which will allow me to control? Therefore, we keep going back and back to start looking what is happening. Yes. Unless we know what is happening, we cannot control it. So the control part is essentially what we need as electrical engineers. But to do this, we must know what is happening. Okay. That's why all the device physics is essentially oriented to tell you how you finally, at the end of the circuit performance, you are doing. And then I will use this knowledge to make integrated circuit chips. Because there I know how many will come and what will be the performance. So I am guaranteeing you some microprocessor speed of say 4 gigahertz will it actually occur at 150 degrees. So I must essentially know whether my microprocessor will work in an environment or not. Let's say my microprocessor is controlling some kind of harmonics in a tank in a Rajasthan desert where the temperature may be 48 degrees centigrade and the whole inside temperature may be even higher. And under those extreme circumstances, if your valve of the gun can fix correctly, you know where to hit correctly. So all these issues do not have direct implications for the day, but this is how we say, like when you go to Himalaya, when you go in the space, you want to know whether our device will work or not work, or if I have to work, what I should do that they still work in the extreme conditions. This is what the physics is all about. Why we want to do? Because we want to do something and then within my interest. Okay, so this is another issue which you must understand. The third thing we see is very peculiar, but it is found that if I plot mu versus carrier concentration, whether Ng or N, essentially say N or P, it has been found that for both P and T, for this curve are not very good because they are not linear, so I am just showing you some very structure. They are not actually linear degree. Okay, these are exponential non-linear. There are some bumps somewhere, some other way. What is it trying to show? That if the electron or hole concentration in the material increases, and typically this value will be say 10 to the power 19 per cc. Let's say this was 1300 or 1350. Okay. This value may be as low as 200 centimeters per volt. From 10 to the power, from intrinsic or 10 to the power 14, 15 per cc concentration, if you increase the carrier concentration to 10 to the power 19, the mobility may decrease by 5 to 6 orders, 4 to 5 orders. What does that mean? Not orders, 4 to 5 times. What does that mean? Why this will occur? Because there are more carriers, instead of interacting with someone else, they will interact with themselves. And they will start defining their relationship with their own next level. If they have larger number, their possibility of it is much stronger. So it is also found that certain devices which are heavy to go, there the mobilities are not very high. That's not very high. This is also another issue which device engineers should know, because mobility changes with temperature, mobility changes with concentration, and in the other day we also show different scattering, mobility may further change for different scatterings, and the last thing we said, which we started first, that if the electric field is also higher, mobility further gets affected by presence of large electric fields. Is that clear? So essentially, mobility is not a constant quantity. But in all other devices that we matter, we assume that we are assuming a condition in which mu is relatively constant. Though in real life, one has to know how much mobility relation one is in. To get this all together, you don't have to do too much these days. My time when I was in first age, so we didn't have any semiconductors. We just were doing some band like that. So we are so happy something new we are learning. So what happens now that there are so many simulators, nice simulators are available. So let's say you are solving a circuit, so there will be a model chart. These are the models of devices. The device simulator will have models which process the self is doing. So for given anything, it has all the formulations which I am talking already stacked. So automatically it will evaluate, it will tell you this is the value, and as it shows it will also find some generally a matrix, the value, you will pick up by extrapolation some value, some by linear extrapolation, some square extrapolation, different numerical techniques are used to get the correct value in between, and they will give that value and solve the thing. So you don't have to really worry whether it is lattice scattered or this, because that scattering part is already partly taken care by us. Is that right? So you don't, but since as an electrical engineer, if you don't know the things, it hurts. So he said, okay, let me know what exactly the things you are talking about. So I want to know, otherwise I can say as a user, I can't care what is happening there. Smaller star yeah, okay. So that's not what we are interested in, because it's some anxiety for us. Oh, why these people are saying like this? If things change, what will happen? So someone else has to do that change also. Why not you then? And therefore, we are trying to do all this as much as possible. Okay, having showed that mobility varies with so many of them, we now shift to another way of address. Maybe since I calculated one, this is of course different from a group, so it's not a great thing, but still to give some numbers. Let's say some calculation of values given to you. Let's say 300 degree Kelvin, silicon is doped with accepted donor concentration of 10 to the power 5 into 10 to the power 16 per 60. And it also has an accepted concentration of 2 into 10 to the power 16 per 60. Therefore, it has both acceptors and donors. They are been asked to find UN, UP. They are also been asked to find therefore sigma n, sigma p, and therefore sigma total. It is of course something not make. Very resistive behavior. Sigma is connected to rho. So any of those parameters can be asked to be evaluated. I am not saying we will evaluate all of them in every case, but any one of them or any two of them possibly will be asked to evaluate. Now, since this 10 to the power 16, both donors and acceptors are much larger than 9, 10 to the power 10. The weight is 1.5 units per 10 is intrinsic Calais concentration. So, in our case, one can say both Nd and Na is much larger than 9. We have solved that problem. Which equation we solved for some calculation for n's? We are interested in n and p. So what do we call the charge neutrality? Nd plus p must be equal to Na plus n. Nd plus p is equal to Na plus p. And the solution for example n times, if you solve, then it becomes Nd minus Na y2 minus plus minus under root of Nd minus Na y2 whole square plus 4nr square 4nr square. This 4 I can take here, this 2 I can cancel. So If you say Nd minus Na is much larger than Ni, this is essentially Nd minus. If you say Nd minus Na is much larger than Ni, so we can always say square of them to be even, or difference to be larger. Therefore, this is roughly equal to Nd minus Na. You just have to know about those values. So 523 10 to the power 16 per cc is your electron concentrations. So how much will be hole concentration? It is N. Ni squared by N. So 12.525 is 10 to the power 20 divided by 3 into 10 to the power 16. And whatever number you get, maybe 7.5 into 10 to the power 3 per cc. Roughly, I don't know. Alright. Okay. So, these are holes, these are electrons. How is momentum rate? How is the NMP? Is this NMP are very large? Not very large. Where the momentum start decreasing? Alternatively, I will give you the curve of N on Q versus mu N. Is that correct? So for a given concentration, go on the graph and figure out what is the mobility if not provided. Then the graph will be. Is that correct? I have N versus mu graph and if says T is 300, I am not bothered with the temperature dependence because T is universally take 300. So I can find mu and T. So what is sigma then? Q mu N, sigma P is Q mu P, and sigma is sigma N plus sigma P. So all calculations are possible, easily possible once I know mobility. Either I should specify it, if not specified, where can I get it? I will give a graph. Concentration versus mobility, what values I got, I see from there how much is the mobility, substitute them there and figure out what is your value of sigma N and sigma T. If I first say further I can do some calculations, I have a semiconductor bar and I apply electric field. Let's say it is entire, same Nd and Na both are there. Then I can also find the current density which is sigma E. E is that if I am given the dimension, this is W and this is thickness. What is the area? What is the area of this cross-sectional area? Current is coming in this direction. What's the area? Okay. W to T. This is your area. So current is sigma A E, and what is electric field? Voltage divided by length. So I know the electric field, I know the area, so I know the current given at a given voltage. So given voltage, I know how much current this semiconductor bar will be flowing if it is loaded with sigma Na and these are this number. Is that clear? So this number, why I showed you this calculation, because these are the kind of things we may ask you as well as you may need in all other future evaluations. So from where we calculate, we just go through our basic equations. We can always calculate which current I am calculating because I have to apply the voltage and carriers are moving as per the direction of electric field. Electrons will move opposite, holes will move in the same direction. Which current I am talking? Drift current in the electric field. So this current which we talk is essentially Ohm's law will be followed. You can say drift current. Now this calculations which I showed you, these are linear, but this also gives you some kind of number. What kind of order of numbers will you get? Because this NDNA which I have given you, this is what the typical most of the devices will have concentrations. 10 to the power 15, 10 to the power 5, 10 to the power 15, 10 to the power 16. These are called normal concentration ranges. Okay, most devices. N and P, when I say, these are the numbers I am roughly talking. If I say N minus, I have symbolization can be done for the sake of just this. N means mid values. Mid value means 10 to the power 15, let's say 10 to the power 17 maximum, but that is also slightly higher. 30. If I say N minus, I am actually looking for less than 10 to the power 13. Less than 10 to the power 13. Closer to intrinsic, but not intrinsic. Other than intrinsic, but less than 10 to the power 13. And it is N minus, and by same argument, if it is of the order of 10 to the power 18 to 10 to the power 20, we say it is habilitated. We say it is habilitated. The heavily doped, moderately doped, low doped, these possibilities can have, and corresponding to place where that plus or minus sign will tell you roughly what ranges you are in. If this is a symbol which we always use, N minus is very good because specific devices will use that. Beyond that, as we say, plus. But otherwise, most cases it is N and N plus. Actually, there is also in book, if it is 10 to the power 18, they say it is N plus, and they say it is N plus plus greater than 10 to the power 19 per cc is called N plus plus. Stronger plus plus. So, this is given because many books have different notations. I may follow some of these notations. I thought in future you should not ask me what number I am talking in some ranges of this one. What is the importance of this number? Because mobility has some direct relationship with this concentration which I start with here. So I am obviously taking you directly the sigma part in the level. That is it. Exactly. If there is a temperature difference, so further take those values and go on the temperature mark and figure out what is the mobility of temperature. So you have to actually evaluate the real situation, whatever the value of sigma. So this data of course is trivial, but just to give an order value, is what it was. Another thing you must know, unless otherwise specified, all devices will be operated at room temperature, 300 degrees, unless stated otherwise. If stated, then use the value, otherwise don't ask what is T. T is always 300 degrees in what called default value. It's always default value. Okay. Let's take another effect which is also possible in semiconductors, very interesting effect. Let's say I have a bar of semiconductor. Now another thing I must want you right now here, I am always showing you as if there is a rectangular bar of materials are used. Nowhere in any device I have any such kind of bars. Say silicon vapor, I will show you something. Bring it, all variations everywhere is possible. So there is nothing called bar. But to get a theory, area, thickness or dependence, you use this kind of picture because it gives you some kind of idea of it. But otherwise, coordinate area, coordinate plane, all that we are interested in, you can answer it with this. Okay. Now here is a bar of semiconductor. Let's say this direction is X. Let's say this direction is Y. Let's say this direction is any direction arbitrary. Let us say again this is my width, this is my thickness, and this is my length. This number has been chosen from that, when I write R, rho L by A. So actually I am using same terminology. Okay. So if you see this bar, now the way I apply, So what is the area here? Cross-sectional area between these two planes if I apply voltage. Let's say I apply a voltage across which direction I am applying? Yes. Along the direction of X, I apply a voltage Vx. If I apply Vx, what will happen to the semiconductor bar is equivalent of a resistor? So it will form V into equal to IR, so it will flow some current, which is J equal to sigma in place. Is that correct? So now, let's say some Ix current is actually flowing in this circuit. I now apply a magnetic field in this direction. I apply a magnetic field orthogonal to both X and Y. So cross. So as if I can say across this I am putting a magnet, not south, so the magnetic field is along that direction, along the that direction, along W. Is that okay? Now what happens? We know, let's say this is a p-type semiconductor or n-type semiconductor. It has number of holes. For the sake of simplicity, we say it is uniform. Everywhere hole concentration is same. Take any hole somewhere here. Now this hole is excited by this electric field. This is the direction of electric field. Please take it. This is minus. This is plus. So what is the direction of electric field? Like this. Is that correct? Therefore the current is also in the same sense because both move in the direction of electric field. However, now these holes, any hole per se or hole transfer, when they move in a magnetic field, they experience a force. What force is what? Lorentz force. You are done with physics. So what happens? Because of the Lorentz force, which is V cross D, actually it is minus q Vy into V. Now this is what Vy I am talking. The point is, since it is force flight, they were actually moving in this direction because of the electric field, but they actually start moving upward because of Lorentz force. Okay, that is number 1 shown ahead. Since hole starts moving on the upper side, the whole concentration there is larger. Is that correct? The lower has, as soon as goes to up, positive charge and equivalently negative is coming down. So what is the direction of electric field which is here? Because more holes on this side than lower. So I create an electric field. Positive negative is essentially will give you electric field. This electric field is in the direction of Y down, Ey. So what happens? As long as holes are not sufficient, so that the Ey is not sufficient, they will move. Is that right? But as soon as Ey reaches equal to the, it is also creating a force. What is the force Ey will do on the holes? In the direct 2 into Ey. Now this 2 into Ey, and you have a Lorentz, other part of the Lorentz force because of the magnetic field, they will start compensating each other. So as soon as Q in Y reaches the value of Q in Z, there will not be any motion. So essentially, since there is no actual Ui being applied by us, after a while when the Ui is in Q in Y, essentially I am saying Q in Y is equal to Q in Y Z. Okay. Sorry, not Dy. Which direction it is? It is in this direction. The carriers are moving in this direction. So X. When this happens, we say there is no more hole will move, and therefore essentially electrons hole will keep moving normally without any influence of magnetism. Is that correct? For a while there will be some this. But that means if there is an electric field, essentially you are telling that there is a voltage across y direction. That's why UI has been created. What will be that voltage? That voltage, let's call a symbol called VH, divided by T is the E1. Is that correct? So if I really apply a current across this device by applying Vx voltage, I apply magnetic field of Z, I can actually monitor the voltage across the upper and lower plates. I may actually get value of some potential across this along this direction. Is that clear? And this voltage is called Hall voltage. The effect is called Hall effect. Actually, you may never apply magnetic field in most circuits. I won't say never, never is not correct. But in general. So I am interested. The problem was slightly different. This was the idea came from this. He always said that if I load a material with NB or NA, NB is the NA is the piece. But this is your only in a junction. Because he calculated somewhere from Q is equal to UN sigma kind of thing. But sigma itself was so many other functions. So one doesn't really know it is only N is NB or E is NA. So we want to really know how much is the real carrier concentration. The reason is other elements. If I load a material by NG atoms, let's say occurs, my idea that all of them will be sitting on this substitutional side is to replace silicon sides so that they can contribute one electron is too much thinking. Some of them may not sit into the side the way what I said other day in the single side. So the number of atoms with which I go need not be always equal to number of carriers I generate, I actually information. Exactly. But I am not interested in how much voting you take. What I am interested in how many carriers I get. That's correct. So I want to know what is the real carrier concentration of a given material, and this measurement, this field effect or Hall effect method allows us to monitor this carrier concentration. Is that clear? That's why we are interested in carrier concentration. Otherwise, that's why we are using Hall effect. Don't think that Hall effect is very commonly used by us. No, but all our test areas in the silicon chip, test area is what called, where actual circuit is not there. Every such component which we want to test, mobility, I want to test it, I make a smaller part blocks of that, which I independently monitor. So one of the test blocks is always a Hall, which we call Hall sample, inside the PH. And we monitor what kind of carrier concentration. Then therefore what is, if I know exactly carrier what I am, then you can find the mobility. So I am actually verifying my mobility and electron concentration properties. This is essential in real life analysis because as I say, I am always interested in control. And to do a control, I must know the value first, then only I can control. So this is a relevant technique, but it is also interesting this. So I write, let's start writing little bit of maths. And don't ask me more questions there. Let's write, I would say EY is VXZ. Q2 I cancel. Okay. However, we know J is sigma E or also QNB. But either we can write Q2. So any kind of carrier. So we say if there is a whole current, it is 2P. Now this can be therefore written as, if I substitute this RH, I define a parameter called RH which is 1 upon QP. So JP upon QP is essentially velocity. Which velocity is this? Yes, so that's the velocity I am replacing with this. So I can say this is equal to JP into RH into where RH is? This is called Hall coefficient. This is called Hall coefficient. RH, which is 1 upon QP. What will be Hall coefficient for electrons? 1 minus charge on the electron is minus. So this is Hall coefficient for electrons, and that is for holes. So can you now think what I am interested to know the value? N. RH is related to which value? E1. RH is related to for a given JP, that is, what is this JP? Essentially we write X if you wish, Yx, because I am interested in X direction front. This JPX I can fix, how I fix it? By applying the voltage, I can monitor the current, area is going to be. Area is going to be, so I know J for this. So I know this value. I have applied the fixed magnetic field anyway. So I know what is the magnetic intensity which I have, so that how much is V mu H. V I know exactly, I am monitoring how much Weber per centimeter square the magnetic field is being applied by me. So I know V Z. I know JP. EY also I can monitor. How much is EY? VH upon T. Thickness I need. Okay. So I monitor VH. I know T. I know area, so I know the current. Okay. Since I know J, I know VZ, I know VH, I know T. What I don't know is RH. So I may calculate the RH. Once I know my RH, I know from here or here what is the electron or hole concentrations I have. This is an interesting way of monitoring on sample inside the device what mobility or value concentration I am going to get in this device. Is that clear? What is test area is called? Whatever is done for whole surface area devices, equivalent all of them are got on a measurement area. There is one area of the chip is only left for that. We keep only monitoring everything on that. So that if this happens here in real circuit, hopefully everywhere it is happening the same. Monitoring is very important in any circuit performance. Because otherwise, whole circuit I don't have punch where I can monitor everything. But one device I can separately make the same process here, which I monitor, and if the same device is there, if it operates here, it will operate here. This is a belief which essentially doesn't work 100%, but most cases one says okay. So in that point here, so what is the importance of Hall effect? That it can evaluate to a great extent, more accurately, the electron and hole concentration. This is one. Though I repeat, this magnetic fields otherwise are there in these devices in silicon, which uses magnetic circuits. So in that point here, why we need Hall effect? Because in Hall effect allows us to monitor and think in more accurate. What is the other method? I just monitor Q is equal to sigma E, J equal to sigma E current. But then what do I assume N there? I assume N is ND. I ज़्यादा से ज़्यादा बहुत अकल में लगाऊंगा तो ND minus N equal. But that time I am doing. Right now I independently can evaluate electron and hole this. Therefore I can say I am much more accurate in monitoring the concentrations. This is interesting. This, if you come to any kind of a device lab or we call it labs, this is one measurement which we do. So I'll leave one instrument which you think over, which is very called, if I am given material, how do I know it is N type or P type? No, I don't have Hall number. I am here sample, there is no Hall measurement can be done. It's a wafer. So I figure out, I take a wafer, and I apply a current source. I should not say, I should say current source. And there are other two probes, these are all 4 probes. And between these two, I monitor, I put a galvanometer. This is I say I give an answer, I will not explain it, think of it what I said, it's not only. If this material is P type, this galvanometer reading goes to the right. It is simple as that, right? If it is N type, it gives something to the left. So by just seeing which way the reflection is, I know the silicon is N type or P type. This is called hot probe. The only thing I do here is before I actually give this current is sufficiently large that the point where it becomes a little hot. So one of the probe is sometimes really heated by the flame. That why heated. As you know, loading now this why one gets N type and P type. Why I am doing all this for 2 reasons I am asking you. In here, if there are electrons, let's say they are in one direction, but there is no real hole. So why should we go to the other side? Only electrons. So the paradox here, you must think why I am saying so, is essentially 4 probe methods or hot probe methods shows that there is a positive charge which is moving on the other side. Is that correct? But in real life, there is no hole. At least it shows that there is a hole, otherwise why should it go to the other side? If you are one can say that there is no hole existing in your sense, then this could not happen. But this proves that this is essentially shifting. That means poles are carriers whether you like or you don't. Same way, if you look at the hot probe, since RH, if you see N or P type, this polarity will change. This polarity will change. So which means, yes, there are positive carriers, there are negative carriers. But in some way, all the time we are doing this, only electrons can move. In a valence band, they jump from one position to another, so there is nothing called hole. But this proves that there is more to it than one makes it. Carriers do exist. A positive charge motion is seen both by Hall method and also by hot probes. Essentially, there is more interesting things can be found by probe at all. Why should the other side choose for reflection? If there were electrons, the reflection should be only one way. But it does show reflection on the other side, showing the free charge and has a positive charge moving. This is an interesting, this is a paradox. I won't say it's a paradox, but it's an interesting question which I leave it to you to think. If you can, someday I will tell you why it is so. But it is still partially paradox. That one cannot really prove that this is so easy. Because what is whole motion quantum electrons? Charge and negative. So kya? But this is only to show what is the, why I keep showing you this example. Same thing happened many years ago. Not so duality in these. Some say electromagnetics are waves, some say they are lights are particles. So duality of wave and particle. Similarly, there is a duality of existence of electrons and force. In real life, only electrons. So why the other? So some experimental proof you have got. इलेक्ट्रिकल इंजीनियर क्या करते हैं अंदर चलता अपना है तो there are some interesting features we should learn because many people believe that एक बार वो इक्वेशन सॉल्यूशन मिल गया तो सब कुछ हो गया, ऐसा नहीं है। Okay. So we have now almost completed the carrier configuration works, mobility related NOP evaluations. We also have already seen one of the transport mechanism, which is due to electric field, and we call that as drift. But we say in the case of devices, there are more than one kind of current input. There are two ways of current. One is current due to electrons, and one is current due to the poles. This is one rotation. But apart from that, there is one drift current, the other is diffusion current. So what is this diffusion current? ऊपर किधर है? आपका नाम लेकर कुछ पता नहीं। Diffusion is a process. It's a random process. Diffusion is a process which is called a random process. The book may have many examples. The simplest example which most will say, or most of you personally say, if you take a small cup of water or glass of water, add an ink drop. So initially the ink concentration is only at the drop of the surface, but after a while it becomes pale pink color and green color. That means the particles of ink finally have reached universally everywhere, and concentration of those two particles are same. Is that correct? This process what we call as the other most famous example is, which I think we should avoid. Hope you understand that. If someone, so I don't want to say this person, but the person sitting at the last starts smoking, initially the smoke will only be there, after it will also become passive focus, because the smoke particles will start finally becoming the whole car, and everywhere smoke will be available. I hope you know. So, what is it essentially say? It says, let us say Mr. Chandorkar is standing here. So, at random I can say, he has at least 50% chance that he may go to the right. He has another 50% chance he may go to the left. It's a probability 50-50. Now, let's say Mr. Chandorkar was here after possibility of one chance. 50% chance he will go here, 50% chance he will be here. If he is already here, 50% chance he will go back. Now, at the same time, 50% from each point will keep going like this, left, right, left, right. So essentially, after a large number of such days, he will be able to reach every different corner of this building. Because that is the probability of every time he can go this way, this way, this way, this way. So then he will straight all around. He can traverse all the class. This is essentially called random walk. This is essentially called random walk. This process is called, is that correct? The process of random walk is called diffusion. Now this diffusion is very important for us. As I keep saying, all bipolar devices have stronger diffusion current than the drift. All MOS devices are stronger in drift currents and much weaker or sometimes zero diffusion. Sometimes it will be modified to sometimes. So the way one look at it, let us say there is some nx number present at x is equal to, it's called delta function. If you wish, you can put this in the thing. It has a concentration of nx at t is equal to 0. I put at x equal to 0 some kind of concentration of material, a charge, in this case let's say, at this point. It's called sheet charge. What is sheet charge from other charges? No weakness. Sheet charge. Where is always a finite difference. There cannot be zero difference. Delta function assumes that way, but it doesn't mean it has no difference. Now, if this is the nx f2 is equal to 0, and you just leave it, it is found that after some time, it takes 4 times. Let's have time t is equal to t. The further time elapses, it goes further down. Further time elapses, it may actually happen. And if you keep doing this, at the end, a uniform concentration will be seen after a long time. Is that correct? So this means that as the time, of course, one of the catchword is whatever is the integral nx dx, this is always, this is called dose. Number per unit area is called dose. Dose. Kitna dose diya na? The right. It's called dose. So dose is or density is fixed. But the peak value will keep going and it becomes flatter and flatter and flatter. So this was an assumption that the process is Gaussian. Most natural processes are Gaussian. So we took an example of most cases since it's a random motion, it's natural motion, and therefore it will follow mostly Gaussian distributions. Mostly, please take it, there is called displaced Gaussian. There is called Pearson Gaussian. So modified Gaussian. But in general, I want to know, my interest is, if you take a one profile out of this, and so आपको यहाँ पे एक figure बना के take करें. Let us say, this is the quantity. Only on one side. I take somewhere here x is equal to. Now I know carriers at this point have probability to go to the like product, right? Up to there they can actually move in within the semiconductor. Till they collide. What is the distance between two collisions we call mean free path or mean free length? So there is a mean free time for which there is no collision. So we say they can go left or right in a small distance of L bar average mean free time, mean free path. This is called plus. So if I point out carrier concentrations on this across this, let us say this side in this area are N1 carriers, in this are N2 carriers. I want to know in some kind of a process which is still thermally equilibrium process. Why? No additional stimulus is applied. This system is still in thermal equilibrium. So in thermal equilibrium, what is the velocity carriers can attain? The thermal velocity under is 3 kg by m. Okay. Since they are having some velocity, thermal velocity, if this number is larger than this, it has been found that they will try to go from, as I just now said, the mechanism is particle is polarized. So they will try to go to the from left to right. So there is always a finite probability they will go from right to left first. So at any given instant of time, there will be a difference between the two sides, N1 minus N2. And the change in this concentration will be proportional to this difference. So that's it. And if that we find which is the flux next time, flux and current tension are related. So the first point, what's the flux available to you? Flux is how we define number per unit area per unit time. So if I know my flux density, then I'll be able to calculate the currents. If I know how to calculate, but here, the diffusion will be